Hi, Bobcats. In this video, we're going to take a look at the kinetic molecular theory of gases. Your textbook actually chooses to cover this topic much further down in the chapter. I find it hard to talk about any of these gas laws without actually making reference frequently to the ideas of the kinetic molecular theory. So I've moved it right up front here in this video lecture because I'm going to be talking about these ideas so much that I wanted to just make sure that we're pretty well grounded in them right from the beginning. So our objectives for this video are to explore these 5 postulates or ideas or statements of the kinetic molecular theory. For short, we're going to call that KMT. And the kinetic molecular theory just describes how the particles of a gas move, and I'd like to connect that movement to things that we can see in lab, things like pressure and temperature and volume. The kinetic molecular theory of gases tells us that the particles of a gas are in constant motion in random directions at a variety of speeds. Some move faster, some move slower. That motion also is in straight line paths. The second postulate says that the volume of the gas particles themselves is very small compared to the overall volume occupied by a gas. This postulate gets stated lots of different ways. Sometimes they'll say that the size of a gas particle is small compared to the spaces between gas particles. Sometimes they'll say that the majority of or almost all of the volume of a gas is the empty space between the gas particles. The third postulate says that the forces between molecules are negligible, except when the particles collide with one another. So the forces we're talking about here are intermolecular forces, which we'll learn about in a later chapter. So this postulate sometimes gets described as particles are non-interacting. And then the fourth postulate says that molecular collisions are perfectly elastic. That is, no energy is lost when molecules collide. We have complete conservation of energy. And let's see, the last one says that the average kinetic energy of the gas molecules is directly proportional to the absolute temperature of the gas. All right, let's unpack several of the buzzwords that appear in this statement. So first of all, whoops, I tapped up top, didn't mean to do that. We'll come down below, I hope. We're talking about the average kinetic energy, and kinetic energy is 1/2 mv squared, so it's the mass of the particles times their speed squared. We have to talk about the average because some particles move more slowly, some particles move more rapidly. And we're also talking about the absolute temperature. Whenever you see this phrase absolute temperature, they're talking about measuring the temperature in the Kelvin scale. And so if we're looking at the temperature in the Kelvin scale, the higher the temperature, the faster the particles are moving on average. I'd like for you to pause this video and flip over in your browser to this Phet simulation of gas particles and just play around with it for a little bit. Just some suggestions to help you get started. There's a pump handle over towards the right of the container that will hold the gas. It looks like a bicycle pump. If you pump that one time, you will get some gas introduced into the chamber. There's a slide bar down underneath that allows you to heat or cool the sample, and you can see how the particle motion changes as it heats up or as it cools down. You can experiment in the settings that are up towards the upper right by holding different things constant. So if the volume is held constant and you heat it up, what happens to the pressure, that sort of thing. And really just try anything that you can think of and see what happens. On the next slide, I'm going to actually show you the result of an experiment that I did. So how did it go with that Phet simulation? Hopefully you were able to observe some things with it. The thing I'd like to do here is illustrate something about postulate 5 from the Kinetic Molecular Theory. That was the one that said that the average kinetic energy of the particles increases as the temperature increases. But remember that if the kinetic energy is 1/2 mv squared. There are two terms at play there. There's both mass and volume. And so the simulation gives us the opportunity to look at two different gases that have two different masses. So what I did was I clicked on this button down here. If you click on the one on the left, you get the blue gas particles, and if you click on the one that's on the right, you get the red gas particles when you pump the bicycle pump. Sorry, that's my 17-year-old cat Moose there in the background. He thinks it's time to eat, but he always thinks it's time to eat. Anyway, what I did here was first I pumped in one pump of the blue gas particles, then I pumped in one of the red gas particles, and they're at the same temperature, 300 Kelvin, and that's that's a little warm for room temperature. It's maybe like about 80 Fahrenheit. And then what I noticed by watching these particles move around was that the blue particles were moving more slowly than the red particles. Well, that's because of the mass term in 1/2 mv squared. If the kinetic energy is the same for these heavier particles and for the lighter particles, then the lighter particles have to move faster to make up for the fact that their mass is a smaller number, because we need to still get that same product of 1/2 mv squared for both the lighter gas and the heavier gas. So if the temperature is held constant for these two different gases, the one that has lighter particles moves faster than the one that has heavier particles. So for this video, our objectives were to look at the kinetic molecular theory and then to try to connect the movement of those gas particles to things that we can see like pressure and temperature.